Next speaker is Professor Allan MacDonald. So Professor Allan MacDonald, can you please share your screen? Yes. So he will talk about Moiré Material Insulator. Okay. So he's gonna tell us something about the Moiré Materials. So I guess, so Professor MacDonald, the talk is 30 minutes. I will remind you once when it's about 5 minutes to go. Yeah, so please go ahead, yeah.
There I am. So Shahal, sorry I missed your talk. I was giving a talk somewhere else, and but so you can jump in at any point in my talk if you want to say something, and also Philip, I hope you'll ask me some of those interesting questions too. Okay, so
the gauntlet has been set.
Yes. So yeah, so I wanted to start by making a few comments about using Moiré materials to simulate Hubbard model physics, and also perhaps to propose a definition of Moiré materials. So this is actually a slide from a tutorial I gave at the March meeting in Boston back in the pre-COVID world. And one of the, this enumerates some of the 2D materials which you could imagine at that moment making moires out of, which includes, of course, graphene bilayers. We just heard about, and includes these transition metal dichalcogenide semiconductors. And the point I want to make here is that I want to, among 2D materials that have Moiré patterns, I want to distinguish the case of semiconductors and semimetals, by which I mean materials in which all of the electronic states are that we're interested in a given energy range are bunched together in a small region of momentum space, and or perhaps 2 or more small regions in momentum space, which we will distinguish by a Valley index. So the point is that when the electronic states are bunched together in momentum space, they have no capacity to resolve atomic length scale properties in the system. And the only periodicity that they're able to, that affects their properties is the Moiré length scale periodicity. So in the case of semiconductors and 2D materials with a Moiré pattern that are semiconductors or semimetals, they're described by a Hamiltonian that's periodic, that has the Moiré periodicity, and therefore they're artificial two-dimensional solids. And I want to propose reserving the word Moiré materials for these artificial two-dimensional solids. And in these artificial two-dimensional solids, there can be different systems we might identify, and I'll talk about a couple as I go along. Then there will be some number of bands, including groups of states distinguished by Valley indices that are present in the energy range of interest. And those can be, in these effective models of these Moiré materials, those act like some discrete internal degree of freedom, which I will refer to as a flavor index, spin or Valley, for example. Okay. So I'm going to, the simplest example of this, one that we originally proposed as a artificial material that can simulate two-dimensional Hubbard models is the case of a hetero bilayer, two different semiconductors, two different two-dimensional semiconductors, tungsten diselenide and molybdenum diselenide. And so these systems are simple because the states near in the energy range of interest is the top of the valence band, which is at a different energy in the different materials. So it's just the states that are basically in one of these two-dimensional materials. And as you all know, in a single layer of these TMDs, the top of the valence band is at the Brouin zone corner. Because of spin-orbit coupling, there's only one state at spin-orbit Brouin zone corner. And therefore, for every momentum measured from the corresponding valley, there are only two states that you can distinguish by valley or spin, because spin and valley are locked. So this maps to a system with a spin-a-half degree of freedom, like, a one-band Hubbard model. And what all the Moiré pattern can do there is define some energy, some effective potential for those 2D states that depends on stacking sequence between the layers, which varies periodically in the Moiré pattern. So it's two-dimensional. It's basically two-dimensional particles in a periodic potential, and of course in the Moiré, that periodic potential telescopes out from the microscopic length scale for stacking to the Moiré length scale, the large length scale on which the stacking changes. And so these are the points I was mentioning. I want to comment on this point, universality. So the idea we had when we wrote this paper, and maybe being influenced too much by our experience with graphene Moiré superlattices, is that the potential experienced in this Moiré pattern would be universal, and so that Moiré potential, in this case, if you assume it's smooth, as we argued, then it can be approximated by just the first shell of reciprocal lattice vectors. And when you use the symmetry of this system, it turns out that you only have two numbers, free numbers, to characterize this potential, basically a strength, and the other parameter you can characterize as the energy difference between the triangular lattice point and let's say the shape of the potential as it varies through the Brouin zone. For example, this chi is some kind of number for the complex Fourier coefficients of the expansion of the potential, and there's a special value of this which corresponds to a honeycomb lattice that I'll come back to in a moment. And the universality that we argued for was based on the argument that when you change the Moiré periodicity, all that changes is the length scales, and the modulation strength's the same. And I think we know now that that's not perfectly true because of, that it is probably actually quantitatively important very often that the lattice relaxations mean that the Moiré effective periodic potential in the Moiré pattern actually gets stronger as you go to smaller twist angles. So here's an example which makes the point that these systems are a realization of a Hubbard model. These are states at the top of the valence band, written not in whole language, but electron language. So this is a flat mini band for holes at the top of the valence band. And if you look at the wave functions in this flat band, then they have a nice Wannier function that and you can easily, if you truncate the Hamiltonian, the Hilbert space just to this band, you can easily derive a Hubbard model that describes the system, and estimate the interaction strength and the band shape and so on. And okay. So that was a triangular lattice, and I'll come back and make a few more remarks about what kinds of Hamiltonians you can realize in these systems in a moment. But let me take a moment to remark that we've recently realized that you can also realize two-dimensional honeycomb lattice systems, and these have not been studied yet experimentally, so far as I'm aware. These appear when you have homo bilayers. In other words, two identical layers of TMD, so that you have a layer degree of freedom in addition to the spin degree of freedom. But it turns out, our original thought was that hetero bilayers would be complicated because you have a layer degree of freedom. But what happens in this case is that if you look at the states near the gamma point in the Brouin zone instead of near the K point in the Brouin zone, then there's as people know in these TMD materials, there's very strong hybridization between layers at the gamma point in the Brouin zone. And what that does is it creates a strong avoided crossing, if you like, strong hybridization between the two layers. And the states can be classified in terms of a parity quantum number under mirror symmetry of the bilayer. So you split basically symmetric and antisymmetric states in such a way that there's a broad region of energy over which the relevant states are symmetric combinations of the two layers. And because it's symmetric combination of the two layers, it turns out that the effective potential that describes them has honeycomb lattice periodicity, has C6 rotational symmetry instead of C3. And so that is interesting, I think, because it gives you another class of systems to investigate Hubbard model physics. Importantly, one that is a bipartite lattice that does not have magnetic frustrations. And this is a calculation of actually band widths and band separations for these gamma valley TMD systems. I'm not sure if somebody's trying to interrupt me. They're quite welcome to do so if so. Yeah, let me keep going unless somebody says a coherent word. So you can easily, the potentials that the electrons see in these, it's just a particle with a mass and a periodic potential, and that periodic potential has a minimum somewhere, and the low energy electrons get trapped in those minima. And you can approximate the wave functions by harmonic oscillators and associated the lowest band with the lowest harmonic oscillator state. That picture works very well for the Wannier And so using such an estimate, you can give, roughly estimate that the width of the bands varies with twist angle. The bands narrow very quickly with twist angle. And also the separation between the bands, another energy scale, which you might want to have control over, also varies with twist angle. It varies linearly with twist angle. And you can see here when you go to small twist angles where you have very localized bands, this is basically, harmonic oscillator states. The atomic orbitals, in this case, the message I want to say is are not hydrogenic states, they're harmonic oscillator states. But you still can control the bandwidth, the interaction energy scale compared to bandwidth and band separation. I'll come back in a moment and emphasize that the fact that the confinement of the electrons in these lattices is harmonic and not hydrogenic, not coulombic, is, I think, certainly quantitatively an important difference between real two-dimensional crystals and these Moiré materials. If part of the goal, and certainly part of my hope, is that these crystals will be good for simulating systems, hopefully that difference doesn't always have an overriding importance. The intention of this slide is to emphasize that in gamma valley TMDs, which turns out tend to have stronger modulation potentials, there's potentially an opportunity to investigate different kinds of physics. For example, this is at a small twist angle. This is these are the Moiré mini bands expanded on the right-hand side, and these are basically the this is the 1s orbital of a two-dimensional harmonic oscillator on a honeycomb lattice. And so this has all of the symmetries, rotational symmetry, invariance under rotation about the plane of these s orbitals, the same ones that you have for the pi orbitals in graphene. And so it turns out that these, because it's honeycomb, the lowest band, instead of being singly degenerate as it is in the other case, is in this case, there are two bands. And these two bands have a Dirac point, just like graphene does. So in fact, this system is basically a model of a graphene crystal, but the length scale, of course, is not a few angstroms as it is in real graphene. Instead, it's tens of nanometers or 10 nanometers or so. And the velocity of the bands at this crossing point can be adjusted with twist angle. So you can have strong correlation physics in this artificial graphene system, which you do not have of course, in a single layer graphene sheet. The next sets of bands are p orbitals. So they're on 2D, there are two p orbitals. And so in addition to the honeycomb lattice, you have some kind of orbital degeneracy and a possibility of orbital ordering physics like occurs in a lot of transition metal compounds in this system. And it turns out that the next set of bands are actually a realization of a two-dimensional Kagame lattice. And one point I should mention here is that which is connected to the fact that the confinement is parabolic, not coulombic, is that if you imagine filling this system up so that you fill many bands, then the interaction of the electrons in the bands you're interested in with the bands that are already occupied might have a large importance, even more importance than they do have in real crystals. So if you wanted to look at the physics in these higher bands, you would certainly have to go to small twist angles where these lower bands are very narrow, and hopefully when you put in enough electrons or holes so that the Fermi level lies, for example, within this Kagame bands, that they're still reasonably localized. Okay. So, you know, with that said, when you get to small twist angles, of course, the Moiré material periodicity, I should say, is very long. So with gates, it will be possible to put in not only one or two, or I think in graphene bilayers, for example, what Shahal showed it varying by 8, but it should be possible to put in, you know, 1, 2, 3, 4, etc. sites per atom, and effectively explore large parts of this periodic table which has analogs to the real periodic table, but is based on 2D harmonic oscillators. So I'm going to spend, I think, the last part of my talk talking about bilayer graphene. I just wanted to mention, you know, when the top of the valence band is at the K point, then homo bilayers really do have a layer degree of freedom. And whereas in most of this Hubbard model-like physics, there's no possibility of interesting topology in the band. When you introduce a layer degree of freedom, then you can get interesting topology in the band and states with finite Berry curvature, which we have in a bilayer graphene just inherited from the Dirac points. What I'm showing you now is a exact diagonalization study of triangular lattice case. Metal shows the metal insulator transition. Certainly one of the things that you will be able, should be able to study experimentally in unusual kinds of way in these Moiré materials. And you know, part of the motivation for looking at this with exact diagonalization is the difference between the fact that these are different because of the harmonic oscillator type confinement at the lattice sites instead of Coulombic. And nevertheless, you can easily see with exact diagonalization that there's a very clear twist angle. In this plot, it's driven by changing the screening environment parameterized by some effective dielectric constant. But there's a clear metal insulator transition between Fermi surface states and states with clear Fermi surfaces and states without clear Fermi surfaces. And also interesting, of course, this cannot be probed in great detail with exact diagonalization studies because of the limitations on system size. But if you look at physical properties, like, for example, the metallic binding energy, which is analogous to the double occupation probability in a lattice Hubbard model, you can see that this metal insulator transition, nothing changes very quickly with as you tune across this metal insulator transition, which suggests that if it's first order, which is the uninteresting case, then it's not very strongly first order, and system pretty smoothly transitions between a metal and an insulator. And there's also evidence for spin liquid states near the metal insulator transitions, but perhaps not very clear. So before I go on and hopefully say a couple of words about twisted bilayer graphene and what Shahal was just discussing and Philip asking about, let me let me put out a plea for something I want to read about, an experiment I want to read about, and that is the relationship between superconductivity and doping in these one-band Hubbard model-like systems. I believe it should be possible to answer the question experimentally, is a one-band Hubbard model, is a dope mod insulator in a one-band Hubbard model a superconductor, never, always, or sometimes, and to get a very clear experimental answer to that question. And so I'm very interested in any discussion on that point, what stands in the way of answering that question experimentally. Okay, so how much time do I have left? Yes,
5 more minutes.
None?
No, 5
more minutes. Okay, so I'm gonna have to go quick. And magic angle bilayer graphene, experiment tells us it's often a Fermi liquid. There's a big region of filling factor near neutrality where it's a Fermi liquid. There's a region of filling factor below -2 where these Shubnikov to Haas oscillations tell us that it is, as Shahal was emphasizing, a broken symmetry Fermi liquid state. And but complicated things happen. There are insulating states, which seem to be, as Shahal was saying, it's zero temperature, reasonably well described by this kind of mean field theory picture, in which the gaps open up in the Dirac points of the various spin valley flavors, which are fairly well understood, and these gaps open up even in bilayer, AB Bernal bilayer graphene. But the interesting possibility created by the Moiré superlattice formation is that the bands themselves, the mini bands, have a narrow width and they're widely separated from remote bands, so that you can easily create polarized states in which some flavors are fully occupied and some are half filled and or not half filled, and so these kinds of states with different occupations with different flavors clearly in experiment occur over broad ranges of partial filling of these flat bands, and the weak field Hall effect is one of the experimental probes that gives clear evidence of this behavior. And so my last point, I guess, will be related to this diagram, which is very close, as you see, to what a picture first articulated by Shalal and collaborators. Here, what I'm going to add is a reason why this happens, possibly, and a reason why, in fact, the details of this are very different on the conduction band side and the valence band side. And so this is, fourfold degenerate Fermi liquid, valence band being emptied with a hole-like Fermi surface, and it seems like the broken symmetries are trying to avoid high, basically high density of states, Van Hove singularity regions, if you like, in the valence band. And so to avoid those, as you get close to -2, not necessarily exactly at -2, be interested in what people can say about that experimentally, you have a broken symmetry state, and something complicated happens, but it becomes simple again below filling factor -2, where you've very clearly emptied 2 of the 4 flavors, and you start just emptying the other 2. On the conduction band side, the particle hole asymmetry means that the high density of a states region in the conduction band is much closer to the Dirac point. And so this flavor, in this case, it's not depopulation, but flavor population to fill the flavors, occurs much more earlier in the process. So the particle hole asymmetry is, okay. So this particle hole asymmetry is actually, for example, not described by the band structure model that Rafi Bistritzer and I originally proposed for this system. You have to correct it not only for strain effects, but most importantly, for the non-locality of tunneling between the layers. And it turns out that that non-locality produces this kind of particle hole asymmetry. And the other thing that's very important is that interaction effects of the band on the bands that I don't have time to describe in detail mean that when the band is nearly empty, when the valence band is nearly empty, it becomes very flat. When the conduction band is nearly filled, it becomes very flat. So conduction band wants to avoid being nearly full, and valence band wants to avoid being nearly empty. And that also plays a role in this pattern. And I think my time is up, but I would just throw out there, the possibility of very analogous behavior compared to cuprates, where certainly one of the important pictures of what's going on in cuprates is that in some complicated way, magnetic fluctuations of spin become a glue that binds electrons into Cooper pairs. And here, it's those fluctuations, we know from experiments, including Shalal's, that as you at a very low temperature, the Fermi liquid falls apart, and it falls apart, it seems, because of flavor fluctuations. The system is really, as you go up in temperature, wants to have a localized degree of freedom on each lattice site, and there I think I've used up my time, so let me stop right there. So yeah, back to you, so yeah.
Thank you, Professor MacDonald, for the great talk. So I guess I kindly ask everyone who has questions to raise their hand. The first one is Professor Una Kim. Please go ahead.
Hi, Allan. You mentioned something about, you went over briefly ED calculations on TMD Moiré system for metal insulator transition. Yeah, so what's the system that you're doing, what's the Hamiltonian? Is it like triangular lattice with further range interaction, or if I may ask?
So the philosophy of this, as you know, there are lots of studies experimentally, mainly in organics, in metal insulator transitions on 2D triangular lattice. Usually, let me find some of these slides, usually modeled theoretically in terms of Hubbard models on a triangular lattice.
Right.
And here, what we were interested in was, what's the difference between a Hubbard model on a triangular lattice and these Moiré material triangular lattices. So this calculation is the Hamiltonian is electrons with the Moiré potential that produces the flat bands, Hamiltonian truncated to the flat bands, but with the full, Coulomb interactions acting in that truncated Hilbert space. And yeah, so we were trying to.
This is more like twisted bilayer Moiré case, less like TMD Moiré.
Yeah. So this is, you can map all this fairly accurately to a Hubbard model like system, and but I can say in that language, what is the difference between this system and the Hubbard models people normally study. And the main difference is if you transform to a lattice representation, let's say, is that the non-local interaction terms are stronger than which are normally not included in these Hubbard models, but they actually do play some at least quantitative role here. For example, we find that the insulating states in some regions of parameter space are actually ferromagnetic instead of the usual 3 sublattice antiferromagnetic state. And that's because there are non-local interactions in which electrons on neighboring sites change places, for example, exchange interactions that favor ferromagnetic states. Yeah, so that in lattice model language, that's the main thing, that non-local interaction terms are more important.
All right, thank you.
Okay, so the next one, Professor Philip Kim. Yeah, go ahead.
It was a great talk. When you say that this gamma valley hybridizations in homobilayer, is a gamma valley for big Brillouin zone or mini Brillouin zone? I got confused here.
Yeah, so the label is Brouillard zone. So this is like, molybdenum disulfide or molybdenum disulfide, homobilayer.
I see. But the gamma point is really the gamma valley is a really distances of far, right? Because that is not necessarily kind of direct band gap regimes, the smallest n scale. So hybridization might be kind of quite weak, I guess.
No, at the gamma point in the Brouillard zone, the hybridization between the layers is very strong. And that's actually the reason why, bulk materials have valence band maximum at gamma, whereas when you narrow it down to a single layer, the valence band maximum is at K. And in most homo bilayers, then already at bilayers, the valence band maximum is indeed at gamma. So these should be the low energy states of the valence bands in molybdenum disulfide, disolonide, and tungsten disulfide also, I think.
But the bulk system is a 2H, right? Basically 180 degrees rotated and stacks. But here that you assume that it was kind of close to 0 degree twisting, not 100. Basically, it's not twisting from the 2H, right? But still, still you expect to see that strong the gamma valley hybridization.
Yeah. So this is, I'm going to say the wrong thing if I try to be too specific here, but this is for one of the 2 stackings that you can make of the small twist relative to one of the 2 stacking of the bilayer.
Great. Yeah. Thanks.
Okay, so we are officially, the session ends, but we can continue the discussion. So if you, want to take a break, that's okay. But now, next question is from Zhong Yu. Yeah, go ahead, please.
Hi. So you mentioned about the non-locality of tunneling when you're discussing about this difference between filling the conduction band versus the valence band. Can you elaborate that further? I wasn't sure whether I understood fully.
Yeah, so this is, you know, this is I think I had a slide. Maybe I don't have it. Yeah, so this is, you know, this is something that was taught to me by the Harvard Electronic Structure Group, and particularly Stephen Carr. And, you know, in the ab initio calculations, there are there are a couple of differences compared to the a model that Rafi Bistritzer and I originally wrote down. One thing is that the flat bands are in the ab initio calculations more widely separated from the remote bands, and that property can be understood just in terms of strain effects, which weaken tunneling between the AA sublattices. But in addition to that, there is clear in the ab initio calculations of particle hole asymmetry, and in which the you know, the separation, for example, to the remote bands is smaller on the valence band side than on the conduction band side. And the observation that, you know, that Stephen Carr explained to me is that that can be, that effect is captured by a simple two-center approximation in which you imagine the tunneling between pi orbitals just depends on the distance between them, let's say. But in the, when we originally derived the interlayer tunneling model, we replaced all of the momenta by the Brouin zone corner momenta. And so we ignored the dependence of interlayer tunneling on momentum. But we know that interlayer tunneling, Fourier transform of the real space interlayer tunneling gets weaker at larger momentum. So you can use one number to characterize the shape of the curve. And that's the approach that we've taken. Just, you know, take one number and fit it to some of the things we know, mostly fitting to experiment. And yeah, so the detailed form of that, you know, I described it as non-local interlayer tunneling because that's the way I think of it physically, but the precise approximation is specified in the preprint that I referred to. Okay.
Another question is that, in general, I think you're considering pretty large dielectric constant. Is there a reason for that? Because I think it's much larger than what's usually considered in the graphene material.
Yeah, so that's true. And, you know, so we know, let's say, the dielectric constant, you know, maybe, you know, if you just took the dielectric constant, the appropriate dielectric constant of HBN, you'd get an inverse dielectric constant somewhere bigger than 0.1, certainly. And whereas, you know, the number we used in most of these calculations is several times smaller than that. And we know that part of this is due to you know, the fact that there's additional screening in the typical environment, certainly from the gates. But I think a large part of it is also due that, you know, that the interactions are just generally speaking weakened by screening effects that aren't included in these mean field calculations. So we regard it as a fitting parameter, and the number we use is, you know, sort of gives bandwidths similar to what people measure in STM.
Okay, thank you.
Thank you. And the next question is from Shunfeng, and we kindly ask the people who have asked their questions to lower their hands. Thank you. Yeah, Shunfeng, go ahead.
Hello, Professor. Thanks for the talk. I have a question also regarding the twisted HOMO bilayers. It's a little bit naive, but can you give some suggestions about how to experimentally probe these emerging band structures and the D6 symmetry, like especially for the optical approaches?
Yes, so yes, I have a very simple answer to that question. I think, you know, part of your point is that because this is, you know, if the top of the valence band is at gamma, then it's probably not as simple to probe the system optically as it is in the K-valley systems. And so that's true. So I think that probably to make progress with this, you have to learn how to make better contacts. And, you know, so that's not my job. So it's an easy thing for me to say. But I can say that in the gamma valley TMDs, the top of the valence band tends to be even deeper than in the K valley TMDs. So that means the challenge of making good contacts for direct electrical characterization is even more difficult. But, you know, I assume that progress will come eventually in making contacts. I know people are making progress, in fact. And, but in addition to that, another thing that I think could be very interesting is maybe infrared optics, right? The energy scales tend to be bigger. I know I'm not sure if it's infrared or terahertz, but that's certainly something that I would be very, very interested and hopeful that this can be accomplished eventually.
Thank you for the answer, Professor.
Okay. Yeah. Suyang, go ahead.
Yes. Please, Hongkong. Yeah.
No. So,
yeah,
yeah, it turns out that there is also another informal session at the end of the third and final session. So I think that we should give everybody a little bit of break, say 15-minute break before the next session starts. So.
Okay, thanks everyone.
And thanks for the wonderful talk, Allan. Thank you very, very much.
Thank you.